Hello, my name is Daniel Bruce. I am part of the Capstone 2 team working on the AmLight research project here at Florida International University. This is going to be a brief video usage guide of importing our ExactDelay Pathfinder library into your own project and utilizing it for whatever your needs may be. This video will also clear up any confusion for future Capstone students when it comes to completing the integration of our ExactDelay algorithm library into the Ketos Pathfinder N app. With a special note on this, we did start the integration of our ExactDelay algorithm library into Ketos Pathfinder N app. So the import should be done for you guys already, but if not, this will kind of clear some things up and any confusion on how to import it. So first things first, this assumes you've gone through all the installation guides, video guides, before this video. And if you have done that, you can simply import NetworkX as NX, since our library relies on utilizing the NetworkX library and traversing NetworkX graphs. And to import our library, you're simply going to do from ExactDelayPathfinder.core import ExactDelayPathfinder. After importing NetworkX and our ExactDelay algorithm library, ExactDelayPathfinder, you're going to create a new instance or new object reference of an NX graph, NetworkX graph. So G is equal to NX.graph. You're going to create some nodes. This is going to be a very small example topology. We'll have user 1, user 2, S3, S4, S5, S6. These are acting as the switches. User 1, user 2 being the interfaces. We're going to add those nodes to our NetworkX graph object reference, G, that instance of G. And then we're going to form some edges between these interfaces and switches with metadata of the propagation delay between that connection or edges between those switches and interfaces. In network topology, these will be known as links. So each link will have a propagation delay. So this is a very small example of a topology here. And then we're going to add those edges to our NetworkX graph. So this entire code is just a basic small form factor network topology and a form of a NetworkX graph. Now we're going to create a new instance, a new reference for our ExactDelay Pathfinder. EDPF is equal to ExactDelay Pathfinder, and we're going to make an instance of a list. Result is equal to empty list, and we're going to assign our result list with some data, and that data is going to be the result of our ExactDelay Pathfinder algorithm. So edpf.search, to go over the method signature here, the first argument or first input parameter is going to be a NetworkX graph, G, right here. The desired user propagation delay, a path that we want to find that has a specific propagation delay, which is of course specified by the user, that's us. And we're going to want to find a path between user 1, the starting node, and user 2, the target node, or interface if you want to say it in network topology terms. And that path between user 1 and user 2 is going to have a propagation delay, or I want a possible path within our network topology between user 1 and user 2 to have a propagation delay of exactly 160. And if there is no path that exists in our topology with a delay of 160, I want to find the closest one, and that's what we're going to do. So let's run our code. And as you can see, the closest to 160 in this case is 179, and then it's going to return some other results, 128 to 262. And this is if it doesn't find the exact path, it's going to find the closest path to that delay that you want, closest to that exact path with that exact delay. Now the algorithm is going to currently return up to 10 results. Depending on the size of your topology, the number of nodes, in it, or switches or interfaces, and the number of edges between these switches and interfaces or nodes, you may get more results, up to max 10 results, or you may get less results. In this case, for this small form factor of a topologist, small scale topology, we have 3 results. So the closest to 160 is a path from user 1 to user 2 with a delay of 179. So if I wanted to put 179, the first result is going to be that exact path, as we can see here. And as you can see, actually, yeah, no, that's actually correct. And the next closest one will be 128, and the next closest one will be 262. So that is a brief usage guide for our exact delay algorithm library, exact delay pathfinder. Hope this helps. Thank you guys for watching. Have a nice day.